All right, class, so this is the last part of this integrated rate law extra practice worksheet. It's not really an integrated rate law problem, but it is something that's sort of related, and I thought that it would be good for us to practice this. So this problem, it says that the rate constant of a first order reaction is 4.6 times 10 to the minus 4 at 350 degrees Celsius. So we've got a K value, so we'll call this equals K, and we've got a temperature. If the activation energy, so that's something we haven't really seen yet, so activation energy, typically that's called an E sub A, is 104 kilojoules per mole. Calculate the temperature at which its rate constant is 8.8 times 10 to the minus 4. So we've got another K value here. So I might just start labeling these K1 and K2. I think that's a simple thing to do. And then I'm going to sort of look for an equation or some sort of help to get myself started on this problem. So if you look at your equation sheet, right over here, we've got this equation that says the natural log of K2 over K1 equals E sub A over R, and then 1 over T1 minus T2, 1 over T2. And that's going to be the equation that we're going to need to utilize here, because it's going to sort of relate equilibrium constants, Ks, or rate constants, Ks, to activation energies, this R value, and then temperatures as well. So I see this 350 degrees, we're going to call that T1. And then we're looking for a temperature, calculate the temperature, so we'll call this T2, that's what we're looking for, when we sort of have this sort of setup. So let's go ahead and write out this equation. It's the natural log of K2 over K1 equals the activation energy over R. We'll talk about that R in just a second. 1 over T1 minus 1 over T2. And I've labeled a bunch of the information already so that we can start plugging some stuff in here. So I might say the natural log, and I've said this is my K2, 8.80 times 10 to the minus 4th over 4.60 times 10 to the minus 4th equals my activation energy, 104. Now this is kilojoules per mole, and if I look at my constants for an R value, I've got two choices here. I've got this R value that's 8.314 joules over moles times Kelvin, or I've got this R value for ideal gases, 0.0821 liters times atmospheres times over moles times Kelvin. Now, moles and Kelvin, they're the same, but now we have to choose, do we want to use the one with joules, or do we want to use the one with liters and atmospheres? And since this is a given in kilojoules, and I've got EA over R, it seems to reason I want to use the 8.3141, because it has units of joules, and since this has units of joules, I'm going to convert this activation energy into units of joules as well. So joules per mole, so multiply that by 1,000. That's going to be the activation energy that I want to use for this E sub A over R. Now I've got 1 over T1. My T1 is 350 degrees Celsius. We're going to obviously convert that to Kelvin, so 623 Kelvin minus 1 over T2. So now I've got one big equation and only one unknown. So this problem here, basically the setup is just sort of figuring out what all these different pieces are, plugging them in, and then doing a whole bunch of math to sort of get to a final answer. Now, when you see this and you're asked to solve for T2, it can be a little bit daunting. So what I'm going to do is I'm going to tell you the answer. T2 is equal to 644 Kelvin. That is the proper answer. So if at this point you want to just do this calculation yourself, or just this, you're just looking to check, great, you can stop now. But if you want to see how I would actually calculate this, I'm going to show you on my calculator actually, so you can sort of follow along. So if I was going to do this calculation myself, what I would do first is take the natural log of 8.8, make sure we type everything in properly, 8.8 times 10 to the minus 4th, so 8.8 E minus 4 over 4.6 E minus 4, and I get a value there of 0.648695. And that's going to equal this value here, so I'll just go ahead and take 10400, 000 divided by 8.314, and I get 12,509 as my value here, and that's going to be times 1 over 623 minus 1 over T2. At this point, what I would do is I would divide both sides by 12,509. This thing in parentheses, it's always sort of difficult to work with or sort of deal with, so it's easier for me to just divide both sides by 12,509. So to do that, divided by, I would just take and find this 0.648 number, divide that by 12,509, and I get a value of 5.2 times 10 to the, let's check what that is, minus fifth, equals 1 over 623 minus 1 over T2. Now what I would do is I would probably either subtract this over or basically just sort of get all the numbers on one side and leave the variable on the other side. So I think what I'll do is I'll subtract 1 over 623 from both of these. So take this number minus 1 divided by 623. So I get a value of minus 0.001553 equals minus 1 over T2. So just leaving this over here. Now I'm just solving for T2. So basically I'm going to bring this T2 up, bring this value down, and I would find that T2 should equal, so the way that I do this on my calculator would be 1, or really it would be minus 1 divided by that value, and that should give me 643.8 or 644 Kelvin, which is the value that we said earlier, right? So I'm just trying to help you sort of work through this calculation, but this is basically it for this type of problem. You've got one equation, one unknown. It's just sort of plugging everything in, making sure that our units match up properly there.